Hello, my name is Andy Benson, and I am presenting Designing New Operating Primitives to Improve Fuzzing Performance. And this paper tackles the problem of how to improve fuzzing by improving the speed of execution of new test cases, as well as coordination between different fuzzing sessions. This paper was originally published in 2017 at CCS, or Computer and Communications Security Conference by ACM. Before getting into the paper, I want to first introduce the authors and their backgrounds to better understand who made this paper. Going through the authors, Wen Zhu has a PhD in computer science from Georgia Tech, which he earned in July of 2023. So this paper was published during his PhD. He currently is the co-founder of Narya.ai, which creates AI productivity nodes. This is very different from fuzzing, the concepts of this paper, but his research mostly focuses on automation of bug finding. The next author, Sanija Kashyap, was also a PhD student at Georgia Tech at the time of this paper's publication. He currently serves as an assistant professor of computer science at the École Polytechnique Fédérale de Lausanne in Switzerland. His past research has focused on operating systems, concurrency, and distributed systems. Changwoo Min was formerly a professor of Virginia Tech at the time of this publication. His research focused on operating systems and security, and he currently works at Igalia, which is an open source consultancy service. He earned his PhD from Sungkyunkwan University. Lastly, Tae-Soo Kim is a professor of computer science at Georgia Tech. His research focuses on fuzzing, operating systems, and system security. He earned his PhD from MIT. The first question, which you might have, is what exactly is fuzzing and how does it work? Software fuzzing is a testing technique to find bugs and vulnerabilities in programs. In a general sense, fuzzing works by taking an initial group of inputs, called the seeds, to mutate and to find new, interesting inputs. There are three main approaches to fuzzing: white box, gray box, and black box. Black box fuzzing has no understanding of the underlying source code. Gray box has some understanding of the source code through lightweight compiler-based instrumentation, and white box fuzzing has full understanding of the source code and can do more complex operations, such as symbolic solving, to break through conditionals. Generally, gray box fuzzing is the most popular approach as it is lightweight and fast. In the above diagram, a simple gray box fuzzing loop is shown. The random inputs are presented as binary, but this can range from anything from structured to unstructured inputs of different kinds depending on the software being tested. The software under test, for example, a.exe file, then runs this new input, and its output is examined for producing better coverage or a crash. Better coverage means that this input either hit a new basic block, function, or edge that was instrumented in the program. Coverage can also be defined on a more fine-grained scale, where repeated hits of the same instrumentation can make an input seem, quote, more interesting. The most desired outputs from a fuzzing campaign are crashes. For general testing purposes, crashes are bad for user experiences and the stability of applications. From a security lens, crashes can be used to trigger exploits on a target. While some crashes are benign, they can still allow attack surfaces for actions like denial of service attacks. For more severe crashes, these can lead to memory exploits in languages like C, allowing attackers to potentially use remote code execution to create shells. This is a worst-case scenario for a security engineer. Software testing by fuzzing can range from simple programs to entire libraries, such as those tested by libfuzzer. This paper focused specifically on coverage-guided gray box fuzzers such as AFL. AFL is a popular fuzzer, which is shown in the image on the right. It uses coverage-guided fuzzing to find bugs and crashes. To produce new inputs, it uses a variety of bit and byte flips, trimming, and arithmetic operations to find new inputs. It has also been combined with a variety of custom mutators to allow its usage on various applications ranging from RTL simulations of CPUs to GUIs. So this is all great, but to understand the importance of this paper, we have to know how fuzzing actually works underneath the hood. So this slide demonstrates a simplified fuzzing interface based on AFL. AFL makes use of a fork server to coordinate different instances of fuzzing runs. So the most basic fuzzing setup is to just run a program in a loop with a system call fork duplicating a process and exec copying a specific program into that new process. To speed this up, AFL-based fuzzers and other advanced fuzzers use fork servers. Instead of calling fork and exec for every test case, they instead call fork and exec initially to spin up a new process that runs the target program in a harness. Once inside this target program, the harness repeatedly calls fork to copy new instances of the target program to run. This is much faster since it removes the repeated exec calls each execution. Basically, the fork server creates new trials that are in a ready-to-run state in new processes. These processes then get input from AFL's mutation engine, which gives it new inputs that were mutations from previously interesting ones. Each of these separate processes records their own bitmaps based on what edge each test case hits. These bitmaps are independent for each of the test runs, and they are updated against a global bitmap that is stored in the shared memory between the target process and the fuzzer itself. This updated shared memory and the associated seeds are then selected for mutation and fed back into the fuzzing instances as inputs. This is the setup of a single fuzzer running on a single CPU core of a computer. At scale, this process is repeating for each individual instance in a fuzzing run. So what might be some problems with this approach? Currently, most research has been on how to better improve mutations in seed selection and instrumentation. This is because better mutations lead to increased coverage, which helps better explore the program and give more chance to find bugs. Seed selection provides increased diversity at the start of trials, as well as provide better mutation through choosing more fruitful inputs to mutate upon. Lastly, instrumentation can provide more insights into the software, while also speeding up execution if it can be selectively applied or even removed once it is no longer necessary. The authors of this paper focused on the speed of fuzzing execution, as well as coordination across trials on the same system. This focused on repeated fork calls and the synchronization of trial progress. So now that we have covered the general background of fuzzing, let's go into the specifics of this paper. So what problem is addressed? So this paper attempts to solve the problem of bottlenecking fuzzers. Prior to the publication of this paper, computers with 16 to 64 cores did not scale well with fuzzing. This led to wasted CPU cycles for contention in the OS. Note, these trials appeared to run on bare OS and not in specific containers or isolation environments for this paper. Several inefficiencies were identified by the authors. The first was the use of the fork system call. This creates a new process for each fuzzing instance running. These calls include unnecessary operations, such as the updating of the reverse mapping of the physical page, and they stress the global memory allocator. By removing these actions, the cloning of processes can occur much faster. The second inefficiency is the creation of test cases. Each independent fuzzing instance saves its own system metadata and relies heavily on calls to open and create to generate test cases and write interesting seeds back and read loading test cases. This creates file contention with repeated system calls for each process. This is especially demanding on a system when dozens of fuzzers are running in unison and calling thousands of system calls a second. Lastly, this paper identified memory synchronization. As the previous slide showed, each fuzzer synced their memory against their own interesting test cases, but this can also be done across sessions as well. So initially, this approach involved iterating through the test case directories of other fuzzers to determine if the test case had been synced, and lastly, execute the obtained test case to get its bitmap to determine if it is useful. This is computationally draining, as the number of test cases to scan increases non-linearly with the number of fuzzers, and this approach also makes the assumption that each fuzzer uses identical bitmaps to record coverage, which is only the case when programs are identical, using the same instrumentation on the same binary executable. So, how do the authors implement their solutions to this? So the first problem was the efficiency of the fork call. So as shown earlier, current fuzzers operate by using fork servers to run a series of new processes executing the target with new input. This is shown under the structure header on the right, where AFL has different AFL applications that each have their own private directories. Each of those AFL sessions operate as separate instances, which are created using the fork system call. Each of these executions of fork is inefficient for the operating system, since many things get updated, such as the reverse mapping of the child's physical pages, which are used for swapping. These have no real effect on the specific instances of the targets executing with AFL, so less overhead can be done and still provide the same services as before. This again was the approach taken to speed up each execution of the fuzzer in order to give it better odds of finding new bugs. To make this process more efficient, the authors of this paper created the snapshot system call in the Linux kernel. This call works by the target process sharing the user space execution context, or all the current registers and signal masks. The first step is that the system goes into the waiting on block loop and waits for new fuzzing requests as shown in step number 1. When a request occurs, a call to snapshot is made to reserve kernel context and register the callback function as shown in step number 2. In step number 3, the actual instance of the fuzzer is run with the main function until it is exited, returned, or killed. Once any of these 3 actions are done, it enters step 4. This is the epilogue to return to the previous state after the fuzzer is done executing in that instance. This is done with the callback function. To put this in simpler terms, the snapshot function just saves the general context of the fuzzer before the individual instances are started with different test inputs. Once each of these instances run, the snapshot function then restores the context from before the instances were run. To make this function work, several changes were made in the kernel. These included changes to the VMA, or virtual memory area, and the page table system. This system maintains a set of pages that belong to writable VMA and use copy on write to keep original memory status. It does not change permission of mapped writable virtual addresses, which the kernel has not allocated to the physical page. These changes were about 700 new lines within the Linux kernel to get this feature working. And now on to the next problem that this paper addressed, which refers to executing test cases again. So how do we improve memory synchronization across our different fuzzing sessions on these large fuzzing setups? So specifically, when we have different fuzzing instances finding new results that are interesting, how do we best share those with other instances of fuzzers running? This is really important, since if we share the interesting test cases between all other fuzzers, this allows them to have more of a chance of mutating on previously effective inputs. This is better for fuzzing since it allows the fuzzing instances to learn from each other and benefit from the findings of the others. In the current approach, when interesting test cases are shared between different instances of fuzzers, the test cases have to be rerun. This is very slow since it involves the interesting test cases being rerun many times across many different fuzzers to generate bitmaps for each of the individual fuzzing instances. The authors propose that there has to be a better way of synchronizing memory between all fuzzing instances instead of this very intensive rerun process, which is especially harmful when the SUTs or software under tests are very large and very, very slow. So the solution that they presented was shared in-memory logging. So the file system changes accompany the usage of shared in-memory for test cases. So this was done with master test case log that can be accessed by other fuzzing instances as a slave. So this is a circular queue that only the master session can add to, and each slave has its own tail marker as the test cases are synced to each fuzzing session. To add new interesting test cases, a fuzzer can push the test case so that the queue contains the file name and trace bitmap for that test case. When all the fuzzing instances have used the interesting input to update their individual bitmaps, the tail marker of the circular queue is moved forward. The diagram on the left displays this functionality. The queue stores general information about the inputs, such as the test case or file name, metadata and input size, and the bitmap, which shows which parts of the instrumented program that this specific seed hit. By doing this, there is no need for multiple instances to re-execute test cases to get their bitmap information, since it is efficiently shared. As mentioned previously, this makes the assumption that all of our fuzzing sessions use identical bitmaps, which can be true if they are running with the same instrumentation, on the same binary, on the same system. So therefore, under these conditions, this solution lowers the synchronization time so the fuzzers can spend a greater portion of their time executing new inputs, instead of just rerunning previously discovered inputs from other sessions. This change, unlike the snapshot call, was made outside the Linux kernel in user space. This affects the fuzzers directly, so it had to be integrated into AFL and libfuzzer, which were the two fuzzers tested for this paper. So finally, the authors of this paper addressed file system congestion on performance. So how does file system contention occur? In high-powered machines, like those used with up to 120 cores or even more, many files are being created and closed all the time for each test case running if most of those cores are being used for fuzzing. As the number of fuzzing instances increases, the total number of fuzzing test cases increases exponentially, since fuzzers will test hundreds to thousands of test cases a second. File system contention mostly affects the highlighted area in the diagram, specifically the creation of new fuzzing instances and the storage of bitmaps. How might this system be improved so that the file system is not being clobbered by too many system calls within the same directories? To overcome the challenge of file system contention, the authors introduced the dual file system. This approach creates a private working directory for each instance of the fuzzer to avoid contention for accessing test cases and allow them to have their own independent file systems. This is done in addition to having a file system service that periodically checks whether memory usage is going above a set threshold. If this is the case, test cases are moved into the disk file system and they're replaced with symbolic links to the corresponding location on disk. This is done in an age-based model since earlier test cases are likely to have lower coverage and are less likely to be reread. This was an assumption made by the paper, and further research has also been done in this area as well. This change involved several hundred lines of additional code to the fuzzers directly, as it was also done outside of the Linux kernel. When gathering the results for this experiment, the authors expanded the impact of the explored the impact of the snapshot system call, shared test case log, and dual file system on execution speeds of high-powered fuzzers on large computer systems. Their hypothesis was that these changes will provide a significant boost to execution speed as the number of CPU cores on a machine increased. This slide shows the results of the changes made on AFL. AFL benefited from the combination of changes from the dual memory system, snapshot, and shared in-memory test case log. To test this implementation, an 8-socket, 120-core machine with Intel Xeon E7 8870 V2 processors was used. The libraries chosen were from Google's Fuzzer test suite. Both AFL and libfuzzer were tested, and an additional wrapper was created for AFL to test libraries directly. These diagrams show that the optimized version of AFL performs significantly better as the number of processors scale. Some interesting results from this are seen in the bottom center with OpenSSL. Fuzzing this with base AFL actually ceases to function after 90 cores due to severe performance problems from bottlenecks. This bottleneck does not appear in the optimized version of AFL, but it appears with significantly more cores in the 60 plus range for libraries such as libpng, cares, and boring SSL. libfuzzer showed similar results with better scaling, specifically for libpng and boring SSL compared to the base version of libfuzzer. So these results show that their hypothesis was true. They could boost performance by adding in these different operating primitives. On this page, these graphs display more of the inner workings of AFL. In the top left, you can see the performance of AFL with and without the in-memory test case log. The blue line requires for more superfluous executions of test cases and more intensive synchronization, which reduce the number of executions per second. The bottom left figure shows that with the shared memory log, the amount of time synchronizing test cases does not rise above 8.05% compared to around 90% for 120 cores without the shared in-memory log. Snapshot in the top right provides benefits up to a point. The peak around 60 cores is followed by a slight decline in the number of executions per second. This is due to the continued high usage of open and closed system calls, which became the new bottlenecks. Lastly, the bottom right graph shows AFL's efficiency running the libpng libraries with fork compared to snapshot by measuring the number of processes created. As you can see, snapshot produces far more than fork as scale increases. Eventually, it does take a significant drop after 60 cores as well for fork. And lastly, onto a final discussion. In summary, this paper introduced a new way of improving efficiency in fuzzing. Fuzzing is a technique of random testing that involves high throughput of data into the test programs, so increased performance comes from either more test cases being executed or better mutations on those existing inputs. This paper used three methods: improving the fork system call with snapshot, the dual file system, and the shared in-memory test case log to create more efficient fuzzers. At least some of these changes apply to almost all major fuzzers available today, as they have similar base structures and make use of the same system calls and resources. This work showed that these changes were beneficial and greatly improved performance compared to the base models of AFL and libfuzzer, but future work in this area can still be done. Some areas of future research include applicable fuzzers, cross-platform implementation, and fuzzing on VM clusters. Fuzzers that diverge from the standard models of AFL and libfuzzer will have less benefits from these changes. For example, fuzzers that use symbolic execution, instruction emulation, or taint analysis will not benefit. Cross-platform implementation would be a help as the majority of applications are made for macOS and Windows due to their popularity. This experiment was done on Linux, but it would likely benefit more users on those other platforms. Lastly, VM setups will likely have different bottlenecks than regular machines due to the semantic gap between the VM and the hypervisor. This would involve needing different primitives to interface between these entities to ensure that the performance benefits that are found in this system between the fuzzer and the OS would be present between the VM and the fuzzers. With the proposed primitives, AFL experienced a 7.7 times, 25.9 times, and 28.9 times improvement on 30, 60, and 120 cores, while libfuzzer saw speedups of 170.5 times, 134.9 times, and 735.7 times on 30, 60, and 120 cores, showing the benefits of these changes. From the perspective of someone who works in fuzzing, this paper was a nice foray into a unique way to increase fuzzer performance. Most research papers focus on how to better select seeds either through random or custom um, structured mutation to test different programs. By focusing on the application to high-powered machines, the authors took a new approach with the use of system calls added to the Linux kernel and modification to fuzzers. My main gripe with this paper is that these changes are very difficult to implement in actuality. Many regular users are unlikely to manually edit their kernel or the distributions of AFL and libfuzzer, as these are massive programs with dozens of files and large repositories on GitHub. Past research focusing on seed mutation was more user-friendly, as users can easily tweak the mutation strategies, and many fuzzers are designed with that intention in mind. I would have also appreciated a more focused view on examining the effects of the changes individually. It seems like all three changes were lumped together for most of the results, but it would be interesting to see if certain changes accounted for better improvements in different environments. Thank you for listening to my presentation.